Consider the function given by f of t equals e to the t over 2 sine of pi t. What part of the formula gives the amplitude of f? So if you see that word amplitude, that means we are referring to sine as being the function that has an amplitude. So that means the amplitude is everything else, e to the t over 2. What is the period of y equals sine of pi t? Okay, that's easy. So we just do 2 pi divided by b, which is 2. And then it says sketch the graph on the grid below. Okay, so we can do that. So this was the period here, and then I like to take the period and divide by 4. 2 over 4 or a half. Those are how far apart the kind of important pieces are on the graph. So we're going to graph the sine function, but it's going to have important points every half. So sine normally starts at the middle and then goes up to the top, but the top is at 1/2, which is right here. So it's at 1/2, and then 1 is the top. And then, so there's the top, and then the middle, and then the bottom, and then back to the middle. There's your period of 2, so that seems reasonable. And we'll just draw a few more of these here, and then a few on the other side as well. Ignore those dotted things, which are irrelevant at this point. Okay, so then we'll graph here our sine function in purple. See, the graphs of y equals e to the t over 2 and y equals e to the negative t over 2 are sketched below. So let's make sure we're clear. This is the e to the t over 2. And then this other guy is the negative, so flipped over the x-axis. Use them to sketch a graph of f of t equals e to the t over 2 times sine of pi t, and then use your calculator to check your graph. So essentially, we're going to be drawing those purple points again, but we're going to make sure that we have that we hit the dotted lines whenever we're at a max or a min. So first I'm going to draw in red anything that was 0 before, still 0, because we're multiplying it by something, but it makes no difference. Those ones are tethered to the x-axis. But now we're going to look at the max, and the max right here normally is at 1, but in this case it's going to get just a little bit higher. It's going to get up to the dotted line. And the minimum right here is going to get lower. It's going to get down to the dotted line. So there's your minimum down there. And then the next max is right here, and it's going to be way up there on the dotted line. And then the next min is way down here. And then we'll do the same thing here. But now the maxes and mins are going to be smaller than what they normally would be. So normally the min is at -1, but that's too low. This one only gets down to the dotted line. And then the next one, the max over here should be at 1, but it doesn't get up there. It has to bounce right there. And then the next min is here, and then the next max is not very high at all. And so then we're going to connect the dots of all these red things. So it starts with very big oscillations, and then the oscillations are going to get smaller. Something like that. And so I won't graph this on the calculator, but you should double check that it looks the way your calculator suggests it will look. And then let's go ahead and move to the next page. Oh, and one other thing I'll say again, that I don't believe that the maximum is perfectly at 2.5 right here, but I think it's going to be so close that you can't even tell that it's not quite the max. Oh, not the next page, but right here. Is the function periodic, why or why not? So periodic means it repeats exactly. This one does not repeat exactly. Sure, it generally goes up and down, but no copy like this up right here is definitely not copied anywhere else on the curve. So it is not periodic. Since the amplitude changes, it's always changing, and it's not consistent. E, how would you describe the end behavior of f as t goes to infinity and as t goes to -infinity? So I'm going to use our limit notation. T goes to -infinity and t goes to infinity. And then you put the function and then equals. So let's look at the first one, the -infinity one. So as t goes to -infinity, what happens to the y values on the green curve, the green one? So what happens to these y values as you go forever? Well, sure, they're going up and down forever, but they are honing in on one single nice number. And whatever that number is the limit. They're honing in on 0. Even though sometimes it's positive and sometimes it's negative forever to the left, they do get closer and closer to 0, and that's what we mean by limit. Doesn't mean it actually gets there, but it gets as close as we could ever possibly hope. The right-hand side is not so well behaved. As we look at the y values on green, what do we see? All right, the y values go up, and then they go down. Then they go up more, and then they go down more. And so this thing just oscillates more and more rapidly. And so, you know, is it infinity? Is it minus infinity? Well, it's none. I mean, it's so poorly behaved, I can't even say it's a single one of those infinities. I'll just put my brief explanation. This guy has infinite oscillations. In order for the limit to exist, we need to hone in on a single number, and this guy definitely does not do that. Next page. Consider the function given by g of x equals sine of x squared. Use your calculator to graph g in the window -3 to 3 and -2 to 2. Okay, so I've typed in my function. It's here. Grabbed a screenshot and put it here so we can answer these questions. Is the function g periodic? Explain. So the question is, does it repeat over and over again? So, well, it kind of looks like this is the same as this, but they're mirror images of each other. They're reflected over the y-axis, which actually relates to part C. But is it a copy? Does the function over here, so here it goes up quickly and then comes down slowly. Does this thing do exactly the same where it goes up quickly and then down slowly? And the answer is no. So this function is not periodic. It just never repeats. See, what is the symmetry of g and why does it have this symmetry? So it looks like the function is symmetric over the y-axis. And maybe search your memory banks. Is such a function called even or odd? So we call these functions even when they're symmetric over the y-axis. And so why does it have this symmetry? Well, you might recall that in order for a function to be even, we need f of negative x to be exactly the same as f of x for every value of x. So if we looked at, well, I'm going to replace those f's with g's, or other way, yeah, f's with g's. So in this case, we need g of negative x to be the same as g of x. Okay, let's take a look at what g of negative x is. So according to the definition, it's sine of not x squared, but negative x squared. And when you take negative x and square it, well, the negative is irrelevant at that point. So it's really the same as x squared, but oh gosh, that's really just g of x. So there you go. It is symmetric over the y-axis because when you plug in a negative value of x and you plug in the positive value of that same x, you get the same y value. So for example, if I were to plug in like this number right here for x, I get this y value. If I plug in so that's my x, and if I plug in the negative x, which is this guy, and come up, oh, lo and behold, it's the same y value. So that's why it has that symmetry. D, graph g in the window -10 to 10 and -2 to 2. Does this seem to be an accurate graph of g? What's going on? So let's just change our window here. So this one we said we want -10 to 10. And then -2 to 2 is fine. So we'll graph this. Oh, goodness gracious. Okay, so let me scroll up a little bit so we can just see that screenshot at the same time. So I'm going to see the middle part. That looks the same there, kind of like a McDonald's symbol in the middle. So I see that. But then all kinds of craziness is happening. It looks like it's higher here than it is here. It's way low down here. Is this an accurate depiction? I think the answer is no. You know, there's a limited number of pixels on this screen right here on the calculator. And there's just too much action happening in a small space for the calculator to accurately give us a picture. So maybe we'll grab a screenshot of that thing. Let's see. Okay, so what's going on? Too many oscillations. In a small space. order to see an accurate graph. So if you really want to see an accurate graph, you just you can't zoom out as much. You need to be a little bit more selective in terms of your window. So for example, before we were looking at this guy from -3 to 3, and that looked okay, -3 to 3. So how about we go from like 3 to 5? Let's take a look at that. So let's look at the window, and we're just going to go 3 to 5. And so it should pick up right where this guy left off. Okay, so that seems kind of well behaved. Let's zoom out a little bit more. Let's go 3 to 7. Okay, and now we can kind of see what's going on here. These things are getting tighter horizontally. Let's try going 3 to 9. And so we were looking at all of these oscillations. You can see it's starting to kind of break down. The pixels are just, there's not enough of them to give accuracy here, but it just goes on and on like that. And so sure, if you try to go too far, like if I try to go to 20, then it's just not going to be able to show me all of the oscillations. There's too many things happening there. That kind of looks like a heartbeat. I don't know what's going on there. That can't possibly be right, but that's what it looks like. That's calculator's best impersonation of this graph. But if I wanted to know what was happening out there near 20, then I would just have to be a little bit more focused and look between 19 and a half and 20. Oh, well, it looks perfectly well behaved between 19 and a half and 20. Okay, describe the end behavior as t goes to infinity. Well, so that's kind of what we were seeing here. It just goes up and down, but it goes up and down faster and faster and faster. So if we went from like 18 to 20, then we'll see this thing go up and down in smaller and smaller spaces here. You know, like this space here is a little bit smaller than it was here in the beginning. So all we'll say is that there are infinite oscillations, and it happens faster and faster and faster.